let's see if we can add some dimensions, plural, to this, because at the moment what we're doing, we are treating the atmosphere and the planet as one object, a point object, and we've simulated changes in the temperature. This is what happens if you model the atmosphere and the planet all as one big thing. And that's obviously not a very good model. If we're going to do a climate model, you kind of want to see how things vary in latitude and longitude. We're going to do this the way that I did it in my PhD, which isn't necessarily the best way to do it, but it's the way that I did it. So what we're going to do is do a latitude-longitude grid. Instead of having XY coordinates, looking ahead to when I might want to plot this on like a spherical grid, a spherical three-dimensional thing. So what I'm doing here is, and yes, I'm doing this in degrees, not radians, sue me. So what I've done here is generate a latitude-longitude grid. That is to say we're going to evaluate data points at certain locations specified by these lat and long coordinates. The first latitude coordinate here is -90, which is the South Pole. The next one, the increment here is 3, so the next one is then 87 degrees south, then 84 degrees south, then 81 degrees, and so on. And the longitude is going to be 0 degrees from the prime meridian in London, so 3 degrees from the prime meridian, so slightly further east, 6 degrees, and so on. So it's like a 2D grid that's just been wrapped around the planet. But if I wanted to plot this on spherical coordinates, doing it this way just makes it a bit easier. So what I'm now going to do is going to do nlat equals the length of latitude, and nlon equals the length of longitude. Instead of having one value, I'm going to define a matrix. So we're going to have a load of temperature for the planet, starting off at the South Pole, and then as you work along upwards through that matrix of numbers, you're getting further north, so that the top line is the North Pole, the bottom line is the South Pole, and then as you go from left to right in that matrix, you are going from the prime meridian eastward around the world, so that the first column is the prime meridian, the middle column is 180 degrees around the other side of the world, and the last column is the data point just before the prime meridian. So I'm generating arrays here. What I'm doing, these are NumPy arrays, which is just a way of storing a matrix in the computer. And they're all going to start out at 0. So the problem with doing this is actually like a big problem in climate modeling, is when you get closer to the poles, as you say, those data points just generally get closer and closer together until when you reach the pole, you have 120 points that are just in a little circle, like right in the same location. That introduces all kinds of problems because you're evaluating all these different functions super close to one another, and in fact if you're at the pole, literally on top of one another. You have to find a way of circumventing all the numerical problems that come with that, and there are different ways of doing it. In a future stream, what we're going to do is do a Cartesian grid on top and on the bottom, and do some complicated maths where you project, calculate, then reproject. Yeah, so as I said, there are different solutions to it. Some people will not evaluate on a lat long grid. Some people will evaluate on a hex grid. Some people or on just a polygon, like triangles, and find or cleverly stack general polygons in a way that tessellates on a sphere, or approximately tessellates. Some people would do a spectral model instead of a grid model. Loads of different ways you can do it, basically. I just think that the grid method, the plane method, makes sense to me geometrically, and I think one of the objectives with this project is I want it to be understandable. I don't want it to be obfuscated, the concepts to be obfuscated behind code. So I like the idea of doing something that just kind of makes geometric sense. So even if it's not the most efficient solution, I think it's still worth putting in there because it's accessible. We've got the temperature as a grid of the planet, and we've got the temperature of the atmosphere. Right, so this lot is all plotting that's only going to be good for 1. So I'm actually going to be super brutal here and just delete all of that. This is our loop of shit that's going on. So let's not worry about plotting just for now. So what I'm going to do is generate a couple more loops. So what that's saying is for each latitude coordinate, and then the same again for the longitudes. If we want to specify a particular point in this grid for the planet, so the surface, and for the atmosphere, then what we can do is we can specify them using these square brackets to denote that we're interested in something that's going on inside the object. I and J are basically our way of iterating through every single point in the object. So at temperature planet, this matrix of the temperatures, at the 0, 0, so the top left, let's say, it does the calculation. Okay, cool. It does all the other stuff in that loop. Then it increases the J by 1, so it's now at the top row, first column, or second column, I guess. It does the calculation there, does the rest of the loop. Then it moves on so that j equals 2. And so it goes through every part of that matrix in turn. That's the basic calculation. Now, I'm not worrying about changing how the sun varies over the latitude and longitude right now. Let's just get it plotted. What I want to do is generate 2 plots simultaneously. I want to generate a plot of how the temperature of the atmosphere varies and a plot of how the temperature of the ground varies side by side. We defined latitude and longitude up here. So let's define them here again. So we're going to use them as our x and y coordinates. Now what's going to go on here is it's not going to look terribly interesting because we haven't actually defined a color bar. But you can see that what's happening is we have a contour fill and it's varying over time. That's the idea. So far, we have been forcing the ground with insolation, which is just a number. So what I'm doing here is generating a code snippet that's going to calculate how much energy is coming in at a given point of the Earth, so a latitude, longitude point at a given time. So in order to do that, I'm just going to assume that it's only dependent on latitude, so we're effectively assuming it's the equinox. The sun's directly overhead on the equator at all times, but it's going around the Earth. That means then that the value is of insolation is going to be insolation multiplied by the cosine of latitude in radians. Don't worry about that if you don't know what that means. It's just making sure it's in the right unit. And so we return value. So now what we're going to do is go in here. We're going to replace that with solar insolation, a lat I, so the latitude that we're calculating, and time, even though we don't need that anymore. So now what you're seeing there is that variable insolation taking place. So you're seeing that the ground temperature is now higher. Yellow is greater and blue is less. So the insolation is highest at the equator, and so the temperature that it's generating is also highest at the equator and petering down as you get towards the poles, towards either pole. And what's interesting is the atmospheric temperature is, well, as you'd expect, because it's not being forced directly by that, it's being forced from the equator. This is really where you start to run into the fact that until you start adding complexity, the atmospheric part of your model isn't going to be very realistic, because it's just not a good model of the atmosphere. Oh, does it look like the top is restarting? Yes. So it will be, because we haven't defined a color bar. So every time step it is actually updating, it's generating a new figure with a new color bar. And so it's basically shifting the goalposts. Let's say that we have the sun longitude equals time times, so time mod day, 360 multiplied by that, divided by day. I think that's correct. This is going to be cos of ln minus, even functions, that doesn't matter, ln minus sun longitude multiplied by mp pi divided by 180. So what I'm doing here is simulating the effect of a day, but because I've got a cosine function in there, and it's going to be over the full range, over the full domain even, I need to double check that it's not going to be negatives. There we go. That's what we would love to see. Okay, so what I just simulated there was the effect of the sun moving overhead as the day goes on. The sun moves over the Earth, around the whole longitude of the Earth, over one day. And so what I used was a mod function here, the percentage sign, which is, it says, what is the value of t? Is it greater than an integer number of days? Is it greater than 1 day or 2 days or whatever? And if that's the case, it subtracts the maximum number of days that it can from the value of t, even the value of time, such that it's the number of hours through that day that it is gone. Then what it does is, then on this next line, it basically multiplies that by 360. So it then says, right, the sun is at this longitude, because if it's halfway through the day, it is halfway around the Earth. And then it divides it by day to then convert it from a value of time to a value of degrees. But look, so what you can see here is, as the sun moves overhead, it's almost like a tire track nearly called it something much more vulgar, moving over the face of the Earth, and so it's leaving warmth in its wake. And what you can see is the atmosphere, because this is almost like we've had an isothermal atmosphere, isothermal planet. We've just turned on the sun, and then you see this. So you see the atmosphere warming up as it spreads away from the sun. Let's finish up. So this is where we got to. We got to simulating the sun going overhead, and we have the ground. We need to set the titles again. That's fine. So what we have is on the top we've got the temperature of the ground. As the sun goes overhead, it's warming up. You can see where the temperature, where the sun is based here, because we don't have, bear in mind, we don't have any kind of Laplacian, we don't have any heat dissipation or any convection or anything like that. If something is warming up, it's because the sun is overhead. It's literally the most simple, basic thing. When the air isn't moving, it's just warming up overhead. Now, what we're going to see is as well that when the temperature is increased by the sun going overhead, it's actually staying. It's not just warming up and then cooling off overnight, because the atmosphere overhead is also warmed. So the sun looks like it's stretching because the sun started here and then it's moving. It's here right now, I think. It's moving around the equator. This is simulating the Earth rotating. So look, we just hit one day, and we now have this tie flag, and so we have this band around the Earth where it's warmer at the equator than at the poles, and the atmosphere is doing the same thing. So next up, what we can do is, next stream we'll look at dissipating that heat in the atmosphere, and so we can do that by varying the albedo of the Earth, which is to say how much light it reflects. We can have the atmosphere move around. We can have it diffuse heat by the heat diffusion equation, so a Laplacian term, and we'll stick with one atmospheric layer. So we won't do vertical convection, but we can do some horizontal convection. So as it moves, it carries heat with it. We have advection of thermal energy. So that's all stuff we can do in future weeks. I think that's more than enough complexity for one stream at the moment.